Worksheet 7a, statically indeterminate torsion. And when we say statically indeterminate torsion, it means that with only the equilibrium equation, we cannot solve for this problem. We need to have another equation in compatibility of the deformation, and we have additional equation from that compatibility and be able to solve the problem. Keep that in mind. So with that, is this problem a little bit more challenge compared to worksheet 6a and 6b in that sense when we deal with the statically indeterminate structure, in this case indeterminate torsion. So with that, it always start with, like I say, external forces for we learn in engineering mechanics, draw free body diagram on kind of that. So with that, we have free body diagram, and you can see fixes both ends. So both ends have a torsion reactions. So with that, we can draw the body here. The first portion, segment AB, stainless steel. No, it's aluminum, and the second portion are structural steel, BC. So from that we can have that is BC steel, and that one here, and there is a torsion at B. There is torsion at B, and that torsion equal to 100 inch kips. 100 inch kip. And let me assume the x-axis go to the right, because the problem in this case they don't give us where the positive x-axis. We can assume that. And the reaction, as you can see, if with this hold tight at both ends, A and C. So you have a reaction in terms of torsion at the fixed support A and fixed support C, and should be opposite direction of the 100 inch kips. In this case, the 100 inch kip based on the right hand rule is positive. Then the torsion at A and torsion reaction at C have to be in opposite, so to balance, to be equilibrium. So that is common sense that you have it here. So you have that is TA, and similarly we also have TC. Basically that is the reaction at A and B. Everyone with that? So that's what we have, the torsion, and from that we can use the equilibrium equation. So we have sum of R, and recall why we use the common sense here to make it correct torsion direction for the support reactions, because as you recall, for the consistency check incompatibility in the statically indeterminate structure, that the free body diagram have to be compatible with the compatibility diagram. So with that, we try to make correct free body diagram at the first time with the reasonable, with the correct direction of the reaction. So with that, here we have moment about X, and assume positive direction is follow the right hand rule. So we have that equal to 0, and we have that is negative TA plus 100 negative TC equals 0. So from that we have TA plus TC equal to 100, and as you can see, only one equation and two unknown TA, TC, so we cannot solve that. That's why we call it statically indeterminate structure. So with that, we need to use compatibility, right? So in this case, distortion, the angular distortion, or general term, it's deformation compatibility, deformation. Because there are two types of deformation. If you recall, The first deformation is the change in length or thickness or the width of the members. The other type of deformation is the angular distortion, deformation compatibility. And the torsion creates the angular distortion, which is create the shear strain compatibility. Shear strain gamma compatibility. So compatibility with that for fixed exposure. Go back to the note. Go back to the note here for the lesson note 7 with the assumption. For assumption, circular cross-section, homogeneous, isotropic, small deformation, and linear elastic behavior. And then the analysis methodology for intermediate torsion. We first use external force reaction, something we just did with the free body diagram. And then internal forces, deformation capability. Here, for fixed exposed end, as you can see, the total angle of twist from this point to the other have to be equal to 0 because fixed at both ends, they both hold tight. So from this end with respect to the other end, the angle of twist have to be 0. Okay, so with that, go back to here, we have to have the 5 total angle of twist equal to 0. And in this case, we have 5. And in that order, AB plus 5BC. Keep that in mind. And now we can, what is AB and BC? You can plug in and you can see here. So 5AB is equal to, what is the 5AB? It's the internal torsion in AB. So here we just skip the internal torsion. We can go ahead to find out the internal forces first or internal torsion. So let's find out the internal forces, or more specifically internal torsion for each portion. So we can we have AB and BC, so you can cut for portion AB. So we can have, and I do it from left to right, so that here you can cut that, and it can continue for portion AB. Portion AB. So we have this is TA, and between AB the 100-inch skip is not involved. So that we have the torsion TAB, internal torsion TAB, and our X is here. And from that we can have based on the right hand rule, TAB positive. So we have the sum of moment. Then we can have, if we do sum of moment about X and assume right hand rule positive equals 0. So you have negative TA plus TAB. So from that I have TAB, the internal torsion between A and B, equal to TA. And we have that the A and the B there. And similarly, we can cut for BC. For BC. And in this case, we can cut from here. We can do consistently with go down here and some more there, and we have structural steel, and it continue until C. So what do we have? This is TA What do we have at B? We have 100 inch cubes, and that is A, this is B, and C somewhere there. And the internal torsion at TBC that we can TBC, and our X is still maintained. So from that we can also have sum of all the moment about X. Assume the right hand rule follow the positive right hand rule equal to 0, and we have that E negative TA plus 100 plus TC plus TC plus TC. So this TBC, let's rewrite that clear. TBC. So what does that mean? I have TBC equal to minus 100 minus TA. Everyone see that? Minus 100 minus TA. So it will be basically minus 100 plus TA. But why I do that here, as you can see from equation 1, here, TA plus TC equal to 100. So as you can see from that one, from equation 1, we have this equal to TC based on equation 1 above. Everyone see that, right? TA plus TC equal to 100. So from that one, I have TBC equal to negative TC. Everyone good? So from that, I have a I can be able to draw the torque diagram for this case. So let's draw a torque diagram. Excuse me. Torque diagram, and from that here we have X and up positive, down negative, and this is for the torsion T, and it also in inch cube. Excuse me. So we have AB 20 inches, BC 20 inches, so they are the same. So we have P point TAB equal to TA, and it's positive, as you can see there, based on the right hand rules. So it will be top TA, and then go down to BC, it equal to TC, so it go there. So from that, as you can see, it TAB between A and B, A, B, C, and as you can see, this is internal torque, and in that case, it TAB basically equal to TA based on what we did there, and then we have here TBC equal to negative TC. So from that, we can continue with the compatibility diagram. Compatibility. Why we need that? Because as you know, for the 5AB and BC, it relates to the torsional equation. Go back here. Why we need to find out the internal torsion? You have there 5 equal to TL over GJ. Everyone see that? And depends on the internal torsion. So from that, we have to find out the internal torsion. So from that equation here, I can plug with the TL over GJ for AB plus TL over GJ for portion BC have to be equal to 0. That is the deformation compatibility. So now plug in. So that is For TA, actually TAB, actually TA. So you have that equal to TA, because that thought diagram here, TAB equal to TA. Again, we have not TA, not TC, but that is the internal torsion between A and B. And internal torsion between A and B happen to be equal to TA. Between B and C happen to be equal to negative TC. Keep that in mind. So we have TA, and then we have 20 inches each, as you can see for the length. So you can write down here 20 inches. So from here I can plug in it 20 inches divide by for the aluminum. What type of aluminum? 2014, and structural steel. Go back to our there. Structural steel, the Chi is 12.2 10 power 6 psi, and aluminum 2014 T6, same as what we did there, 3.9. So from that we can go back to our equation here. So we can have that go back down. So we can have G, it 3.9 10 power 6 psi, or 3.9 10 power 3 ksi, or 3,900 ksi. And then the J, what is the diameter here? 2 inches and 1 inch, as you can see there. So we can plug in there 2 inches. So we have 5 over 2 power 4, and then plus T at BC based on thought diagram, negative TC. So negative TC, also 20 inches divided by steel. If you recall, that is 11.2 10 power 6 psi, or 11.2 10 power 3 ksi. So or it 11,200 ksi. 11,200 ksi for structural steel, and you can see that. So from that we have plugged down here 5 over 2, and that is 1 power 4 for the diameter of the cross section between B and C, and it have to be equal to 0. Make that, people thought it a 5, but it equals 0. So from that, simplify that equation, as you can see here, that equation have TA and TC involved. So that simplified, so we can have that is equation TA minus 5.57 TC equals 0. And this is the compatibility equation. Let me call that equation 2. And now we have two equations. For equilibrium equation, we have TA plus TC equal to 100. For the compatibility equation, we have TA minus 5.557 TC equals 0. So from that, simplify that two equation, we can solve, right? So now from that, we can have equation 1 and 2. Simultaneous equation. And of course you can substitute or whatever you want, because so simple in here. So you have TA plus TB equal to plus TC equal to 100 from equation 1, and then we have TA minus 5.57 TC equals 0. Equation 2. If, for example, if you get equation 1 minus subtract equation 2, you will get TC and plug in. So from that equation, we can find out TA, these two equations. We have 84.8 inch cubes. And we have TC, the support reaction at there is 15.2 inch cubes. And from that, you can plug it in here, the torque diagram with that there. So now we already find out the ATC. So that is the portion of the, as you can see, of the statically indeterminate torsion. Have to have compatibility of the deformation, and that is something different compared to worksheet 6a. So it's very important. It's more challenge in that case here. And now the question, when we have all of that, determine the maximum shear stress in each segment is exactly the same of lesson 6. Okay, so because now we already know all the internal torsion, then just go ahead to find out stresses that the question asks. So stresses here. So for AB, we have tau max between member and AB, so it's equal to torsion along AB, C for AB, radius in cross section AB, and J for AB, right? So plug in TAB from torque diagram is equal to TA, so you can plug in 84.8 inch cubes. C is 2 inches. J, in this case solid, so P power 2 over 2 to power 4. So from that it equal to tau max between AB equal to 6.75 KSI. Are we done yet? For each, what did the question ask? Determine shear stress in each segment. And go back to our lesson. All of these equations have to be linear elastic behavior. What does that mean? It have to be inelastic. So that the shear stress in here have to be less than the yielding shear stress. So check with the aluminum. What is the yielding stress rate? Check with the appendix B for the yielding shear stress for structural steel. So let me pull out here appendix B. What do we have? We want to know what is the sigma yield for aluminum and what is the sigma yield for structural steel. Okay, so let's go back to our diagram. Again, yielding shear stress, not tension shear stress. Here, structural steel is not 36, it's 21 KSI. Everyone see that because we talk about shear. And aluminum 2014 T6, it will be 33, not 58. Keep that in mind. So we go back to our here. It is 33 and 21. So that is 33 KSI and 21 KSI. And we have to check that here, whether it have to be less than the yield stress, and it actually less than that. Sigma aluminum yield, which is 33 KSI. What does that mean? It's elastic behavior, right? Oh no, that is not sigma. We're talking about the shear, so it will be tau tau, 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 right? We talk about shear stress. So what does that mean? It in elastics, it less than, so elastic behavior. What does that mean? Okay, same as our good assumption that is a linear elastic behavior. Similarly, for the shear stress maximum between B and C, it equal to T BC, CBC, so the radius for cross section between B and C, and J BC. So here TBC equal to negative TC, and here because the shear stress, as you can see, we just compare with basically the absolute number. Only angle of twist, then you have to care with the negative, right? TBC is negative, TC which is negative 15.2 if you do the angle of twist. But for this one, only the shear stress, so only compare with the magnitude of the yielding shear stress, so we can plug 15.2 1 inch for the radius of cross section of that structural steel, and then JBC equal to pi over 2 1 power 4, and that is equal to 9.68. Let's go down to another line that makes similar to the other one. So you have tau max BC is equal to 9.68 KSI, and we have to compare with the tau yield strength instead of shear strength for yielding of the structural steel. It equal to 21 KSI. What does that mean? It also in elastic behavior, which is okay. So we can stop here. If it's not, then it maximum equal to the shear yielding shear, which is 33 for aluminum and 21 for KSI. So with that, we're done for the first problem of lesson 7, worksheet 7.8. Worksheet 7b exactly similar, but that is composite shaft. So I suggest you to practice using the compatibility of deformation to find out the internal torsion for each. The process should be similar, but the equation for compatibility a little bit different. Go back to the lesson note in lesson 7 to check for that equation.